All right, I think we're ready for today. We're gonna do a little bit of tuning. I do have the printer running. I just had to get the right firmware that matched the screen and the firmware on the printer itself. They had to match, and so that wasn't very difficult. I just didn't want to do it live stream because it could have been difficult, but it was. It wasn't. It was pretty simple. We just had to take apart the screen, which there's 4 screws on the back. You take the back cover off, and it has a SD card slot, and you do the same thing. You load the firmware file for the screen onto a little micro SD, put it in the screen SD card slot, and turn the printer on, and it updates it. So that all works now. It's running an old version of the firmware, though, so it's not super up to date, but we're going to change that through the course of the course anyway. So I'm not too worried about the filament, or not the filament, the firmware right now. We'll get to that in a minute or someday. What we are going to do today is we're going to do some tuning, which if you knew you were going to change firmware like we do, and you weren't trying to like make a bunch of examples of things, then you would get your firmware the way you wanted it before doing these tunings, because when you change firmware, you lose all your tuning stuff. So some of these are mechanical, like physical tuning things to check. So those will be useful regardless of what firmware you're using. But some of them, the digital ones, they will be erased whenever we change firmware. So you'd have to redo them. All right, so let's look at our web page here, and let's check out some of the stuff that we're gonna do. So this is in Canvas over here. I haven't really posted these outside of Canvas. Maybe I can figure out a way to do that on my other web page, my actual web page. But these are all in Canvas. If you haven't noticed, that I have been putting these little tips on each one of the classes. So we've done 3 classes now. The first tip was level the bed, but not with the level. And we kind of went through and did a manual leveling routine to get the bed more or less flat, trimmed with the machine. So we did that. Class 2 didn't really talk about this particular thing, but anytime you're printing, got everything set up and tuned, in general, you can get a better print. And I said better print. That might need to change. Let's actually change that right now, because you can always get a better surface finish. Let's make it that. That's a little clearer. Surface finish. All right, there we go. Get a better surface finish by printing slower. There are cases where surface finish doesn't matter. You know, you're just trying to crank out a part really fast. You're going to use really thick layers and print fast, speed, high flow rate, and you just want maybe it's a test part, or maybe it's a part that doesn't appear anywhere, so you don't care what the surface finish looks like. But if you're worried about surface finish, you can almost always improve that along with other things by printing slower. And today's tip was clean your print bed for optimal print adhesion. So invariably, you're over at your printer and you've got a print that you need to remove from it, and you're putting your hands down on the let's go to our printer. You're putting your hands down on the bed. You know, you're doing stuff here, and you're probably getting grease from your hands on the surface of the printer, so the print surface, and that grease is going to make adhesion difficult. So what I do is I take the oh yeah, let's look at, I don't know how I'm gonna get this on the camera. I got one of these little boxes. This one came from Hobby Lobby. It's upside down there, but $9. And it's, you know, got a locking lid. It's not airtight or anything, but it doesn't need to be for what I do with it. This one is new for this printer, so it doesn't have much in it yet. I've got calipers, which we'll use today. These are digital calipers. I actually don't like digital calipers because at some point the battery's going to die, and it's always an inconvenient time, so I don't really like them. I'd rather have manual ones, but here at home they're the only ones I have that are metric, or at least can be metric. And most every measurement you're going to make on the printer is in millimeters. So it does make sense to have a metric caliper. You could get away with a ruler, probably have that in there too. But what I was talking about is cleaning the print bed. I use these little things right here, just like, you know, when you're cleaning up before you get a shot or something like that. You can get these off of Amazon for nothing. Well, not nothing, but they're really cheap individually. And then you can, we'll talk about these pieces later. Then you can just clean the surface pretty easy. And they're isopropyl alcohol. The other thing, I just don't have it here, but if you get a little spray bottle and just put isopropyl alcohol in it, then you can just spray your bed and clean it that way. These are just nice if you have them because they're always ready, and then you just throw them away. It did actually get some dirt off of there. I don't know if you can see it. It's kind of bright. But it did actually clean the surface, not just grease. There was dirt on there. So clean the print surface. You got it level, hopefully. And again, level means that the nozzle, if I can get the nozzle in the picture, the nozzle is equally the same height above the bed. This one does have a glass surface on it. So the glass surface is generally pretty flat and generally not too susceptible to heat deflection from the aluminum plate underneath it. You know, because it's glass, it doesn't change as much as a piece of metal would with heat. So it does have the glass bed on there. The downside, so just since we're talking about glass beds, the downside to the glass bed is that it's heavy compared to other options. And we'll put some other options on throughout the quarter. But it's heavy, which this is a bed slinger, meaning it moves the bed back and forth. And that extra weight having to accelerate, decelerate, change directions means you're even more limited on your maximum printing speed without ripples in your print surface. So that's the downside to the glass bed. This one is a thinner glass bed. It's still 2-3 millimeters thick. They make thicker ones, so this is a thinner one, but it's still heavy compared to other options. All right. Oh, I tried this guy, and it worked. Got this print out, so I got a little calibration cube. These little cubes, typically, if they're called calibration cube, they have two main features. One is yellow is a horrible filament to show. I probably should get a different color because it just doesn't show up very well. But they have letters on them that you can know which orientation they were printed. I guess it would have been that way. And you can look at the letters and see ripples in the letters if you're printing too fast or you've got a belt loose, something like that. And each side is 20 millimeters, so you can take your calipers out and measure, are they close enough? Now, don't be worried if it's 20.02 millimeters or if it's 19.8 millimeters. You know, if it's close to 20 millimeters, you're probably doing it right. The height, so in the Z direction, this way, that's one that you probably need to pay more attention to. Let's see if we can make this show up. I'll zoom in. Yeah, I think you can see that. It's kind of blurry, but see the bottom of it, how it curls out right there? That's called elephant's foot. And what it means is that when you printed, your nozzle was too close to the bed, and those first 2, 3, maybe 4 layers were squished right on top of one another in the same space, and they spread out and created that little elephant's foot shape around there. So that's going to do 2 problems. Well, one good thing is that it squished it down to the bed, so it's probably going to adhere really well. The 2 bad things are that it's going to be shorter by some amount. So let's get our calipers out and see. I didn't actually measure this one. So let's zoom back out. All right, so our battery is working. It is not zeroed though, so let's zero it. And let's measure. This is supposed to be 20 millimeters. 19.86. So it's shorter than 20 millimeters. It's in the right range, so it's not like there's a completely wrong thing, but it's short because those first couple of layers were squished more than they should have been. So it makes it shorter. And if this part that you're printing, if it needs to fit into something, this bottom edge is going to be wider. It's going to be wider, not this much wider, but it's going to be wider than what the hole you made for it. So it's not going to fit right. So you do want to kind of adjust your nozzle offset. How far is the nozzle away from above the print surface when you start printing? Too close, you'll get really good adhesion, but those first couple of layers are going to be squished out, and your part's going to be shorter than you expected. All right, let's go back to the web page. So I've put a couple of things here, some links. Oh, this vase model. Let's go to, this is just a STL file. It's got printables. So this file right here, I use this one for printing a new filament. I'll get these little samples of filament there that are only maybe 20 meters long. So they're not, you can't print much with them, but it's just to sample the filament. And I'll print these things. Now the model here, I actually printed 50% scale of what the model really is, because I'm don't want to take it forever to print, and I don't have that much filament on the little samples. I'll show you some of the samples. Here's one. So they usually something like this. So you get that much. This one doesn't say how much is in there, but it's not much. It's just a sample. And so I'll print this because in vase mode, we haven't talked about that, but basically it's just a one-wall print that's spiralized. At half scale, it takes around an hour to print. So maybe 45 minutes to an hour, depending on your settings. And you can get a sense for how the print material is going to look, what it's going to, different shadows and reflections on it because the thing's faceted. So I've got some of those. Let's look at them real quick. Oops, Ultima. We don't need Ultima. Let's see. Let's go here. So here, this one is a shiny filament. And again, I don't know if you can tell, but there's only one wall. Oops, one wall in there. So these shiny filaments, they're really cool. They like, this has 0.3 millimeter layer lines thickness, so it's really thick layers, but they're really hard to see. The shiny filaments lay down really well, and obviously they're shiny. The problem with them is that oh, I can't think of what it is, but the additive that makes it shiny, can't think of what it is right now, but that additive makes the layer adhesion a little weaker than normal. So shiny materials are not good for structural parts. So if you want the part to be under stress at all, don't print it with one of the shiny materials. They're not like super weak. Like I can add some force to this, but the layer adhesion on these, if it's a real structural functional part, then you don't use shiny for that. So that's what I print. I've got a couple others over here. This one's just PLA that's shiny. This one is a little bit transparent and flexible. This is polypropylene. So you can actually print polypropylene. That's like the milk jug material. And it's food safe if you... So food safe in 3D printing, FDM 3D printing is a little bit tricky because most of the actual materials don't harm food or anything. Most of that's not the problem. The problem ends up being like bacteria can grow in the little layers. So you don't want liquids really or anything. Really the only things that I ever print that interact with food are one-time use cookie cutters. So you make some special shape that you want for the cookie cutter, you use it, and then you just don't use it again. Because you can't really wash them with any heat for most materials. PLA, you put PLA in the dishwasher and it's going to melt. Well, not melt, but deform. So it's just hard to clean them in a safe way that doesn't destroy them for PLA. This material has a little bit higher temperature that it can deal with, and it's flexible. So it's a neat material, and it's a little bit see-through. You know, it's not perfectly see-through, but you can see inside it. So that's polypropylene. This one has, let's see, this one is the iron, I believe. It's heavier. I know you can't tell that, but it's like twice the weight of these other prints over here. So it is a PLA material that has, I believe this one's iron, and it has ground up tiny particles of iron. It doesn't make it stronger or anything. It definitely makes it heavier, makes it more expensive, and it's just interesting. So you can actually like cause it to patina or rust. You can kind of sand it a little bit and get some the little edge highlights on there. So it's an interesting material. It's not necessarily meant for functional purposes. We will look later in the quarter, hopefully, at we can at least look at the material, but I don't know if we can process it. A material that you can print on a FDM printer. It's super expensive, and you have to have some special equipment to process it, post-process it. But you can end up with solid metal parts after you've post-processed it on an FDM printer. If you want to look at it now, it's called Virtual Foundry or Digital Foundry. I think it's one of those. Virtual is the one I think it is, but maybe it's digital. I don't know. This one is not like that. This one has like maybe 15 or 20% metal particles inside the PLA. It does make it heavier. It's obvious that it's heavier. It doesn't make it stronger in any way. It probably makes it weaker, in fact, because you've got all these particles in here that aren't connected to anything. It probably might make it stronger in compression, possibly, but not in tension. And then the last one I've got here today is a glittery TPU. So these were all printed on not this Ender 3, but another Ender 3. So the flexibles are another interesting thing. Like this one is flexible in a way, like it just has some distortion. This one's like rubber. So I mean, you can completely compress it and then get it back to where it was, the original shape. So these TPU materials, they're a little bit harder to print. You have to go really slow. And we'll maybe talk about some of the settings you can use for those in general, but they will print on an FDM printer. It's not ideal, but it can work. And then you end up with some really cool stuff. All right, so each time I'll probably bring out, I have hundreds of these little vases of different materials, so I'll bring out some different ones every now and then to look at. And if y'all have a particular type of filament that you're interested in, I might have a sample of it that we can look at. All right, now back to our where we were. How do we get there? Might have to log back in. All right, here we are. All right, so we're talking about calibration. So assuming that we have got our printer to where it's turning on and it's basically built and set up, there are some things you want to check to make sure that it's going to give you the best possible print. Some of these are overkill, particularly the ones I've got at the bottom of the list. That's kind of they're at the bottom. But some of them are kind of necessary. So I've got here a general order for calibration. And first of all, make sure you've built everything right. So if I were not using this printer as a like a teaching tool, and I was using it for more of a fabrication type thing, and I was putting more effort into this printer printing really well, then I would probably go in and check the squareness of everything. You know, get a machinist square or some kind of tool that I could measure that things are parallel and square and all of that, because I have had a printer. Let's go to the printer here. I have had a printer in the past where I'm gonna have to move it so you can see, where this piece here was not at a right angle to this piece. And what that caused is it printed okay, and you could level the bed and it would look level, but the parts you got off of it were all skewed. And so it took me a while to track down what was actually wrong. And that can be a problem, you know, if you end up with that. It's easy to figure out. Just print two, well, it can even be these, two calibration cubes or two vertical rectangles. They don't have to be anything special. And then put them back to back. And if they have a gap between them, then they were skewed. You know, if they didn't print both vertically, when you turn one of them around, put it back to back, then they were skewed. Something in your machine was skewed. So I have had that on one printer before, and it was an Ender 3, a version 1 Ender 3. So you could go through and check all the squareness. So how is assembly? Some of this stuff was pre-assembled. So go through. We talked about the eccentric nuts, adjusting those so that you don't have any looseness, nothing's wobbling around. It might wobble a little bit, but it's not drastically wobbling around. You know, check the assembly, even the stuff that was pre-assembled, because it may have not been pre-assembled very well. So do that part. Then do the bed leveling, so the manual bed leveling. So heat your printer bed to the temperature you plan to print at, so 50 or 60 degrees Celsius, somewhere in that range, or off, whichever. And then go through and manually position, you can turn the stepper motors off or whatever, and manually position the nozzle right above the surface of the bed, and turn these knobs, there's 4 on most of these printers, and turn them so that you've got an equal distance between the nozzle and the bed surface at each 4 corners and in the middle. Then go back and also check the middle also to make sure that distance is the same as all the others, because sometimes these beds have a hump in the middle or a sink in the middle, and you have to deal with that. And there's a couple of ways to deal with it. Right now, all we can do is average it out the best we can. If you do have a printer where it's got a low spot and you're not using a glass bed, but you're using a flexible thin bed, you can take little strips of aluminum foil and sandwich those between whatever surface you're using and the main aluminum plate here, and fill in some of the low spots. So you can do that. It doesn't work as well on a glass bed because it's not going to really deform that much. And generally the glass beds are flat already, so you don't have to worry about the humps and valleys too much. All right. Next thing, the belt tension. So your x-axis and your y-axis are both driven by belts, and on this kind of printer. Some printers, they're different, but most printers that we're going to deal with, at least the X and Y are driven by belt. And let's look at those. You can see this one on the front up here. So right here. Now this printer is actually a little bit easier to adjust this tension with, because it has these little knobs that you can tighten the belt or loosen the belt. Let's see. Let me see if I can quickly find. Well, I don't have a little piece of the belt handy, but these are timing belts. And a timing belt means that it has, let's see, I don't know if you can pick it up. Yeah, you can kind of see it. It has little teeth in there, right? So you can kind of see the edge of those teeth. So they don't need a whole lot of tension. In fact, if you over tension them, they will wear out the stepper motor that they're attached to faster. The bearing in the stepper motor, because it'll have extra lateral load on it that it doesn't really need to have. So these don't need a lot of tension. The downside is they need enough but not a lot, is that it's really hard to measure, and it's more of a feel kind of thing. You will find some people on the internet who say that you can tune them, like tuning a guitar string or whatever. And sort of, that's kind of true, but it's equally as bad of an option. There are belt tensioning tools that like you might use on a automotive engine for a fan belt. Those are way too big for these size belts. So there's not a super great way to tighten them down. What I do is I just make sure that they're not floppy. So this is too loose. You know, that's too much slack. And look, see, I can move the belt and the without moving the stepper motor and the bed. You can kind of see it hump up there when I move it forwards. That's too loose. So I would tighten it a little more. That's probably about as loose as I would want it to go. I don't mind it being tighter than that because this is not really applying too much tension or, well, force to the stepper motor. Stepper motor's actually back in the back, way back there. So I would probably do a little bit more. That's probably good. Where it's a little bit difficult to roll the belt totally over. I like to get it all the way over. It's kind of hard. It doesn't slop around when I move the belt back and forth. That's probably a good tension. And so this one also has that on the x-axis over here. It's kind of off the screen back here. If yours does not have these, then what it has is screws that you can loosen, and you take a tool like a screwdriver, pry it out and tighten the screw back down. Those don't exist as much anymore on newer printers, but they are still out there. You can actually print these type of things or buy these type of things as add-ons if your printer doesn't have them. You don't use them much. They just make it easier to adjust belt tension. If your belt tension is too loose, then your motion back and forth is going to have too much slop in it, and you'll get parts with the outer walls that are, you know, they're just kind of unpredictable where they're actually going to land. So they're going to be wavy, and they're going to have ripples in them, and it's just not going to look very good. Too tight on the belts and the stepper motor. So there's the edge of the stepper motor back there. The belt is actually on the end of the shaft of this stepper motor, and you'll put too much force on that bearing inside there, and you'll prematurely wear out the stepper motors. So it's not an exact science, but it is something to worry about as far as one time you need to go in and every now and then just touch them, make sure they're not floppy. And they shouldn't be super tight either. Like, this is fine, like that. All right, so those are on your mechanical side of things. Z-axis alignment. This is actually something that this particular printer I had to deal with. So what that means, let's get the side of the printer. See if we can get a good picture. Let's back up. Okay, so notice I've got the metal coupler here. I went and got one from a kit that I had not used. We had this guy on there and this one, and it worked sort of, but it started slipping, and I ended up with this. I tried to print a benchy, and I ended up with a kind of short benchy where it was printing fine, and then that little coupler started slipping, and it wasn't raising the z-axis. So it worked for long enough to print that first one to make sure the printer worked, and then it kind of, I was tired of dealing with it, so I put the metal one on there like it's supposed to have. So the z-axis alignment, this lead screw right here is, sometimes your printers have two, one on each side. All these little enders by default just have one, but it needs to be parallel to the rail here that the z-axis is moving on. And can you see it? Let's see. You can kind of see it. This little piece right here, those are shims, because without those shims, this motor was too far drawn into the rail, and it was making this rod canted. It was, it was sticking not that far, but it was not parallel to this axis here. And that's a problem. I know the background's all cluttery there. I don't know if I can get it less cluttery. I need something to block off all that. But this rod needs to be parallel to this. If they're not, then they will bind well, and that's probably what happened to this guy. Is it was going along fine, and then that non-parallel between the lead screw and the axis made it to where it was, the Z motor was having to add more and more force to try and lift the Z axis, because the path and the lead screw were diverging, and it couldn't do it. It started slipping, and it was kind of moving up, but not really, and it definitely didn't work right. So I switched over to the metal coupler and straightened out the, well, I didn't straighten the rod. So you do need to make sure that this thing is straight. If you think it's bent, take a flat table and just roll it across the table, the lead screw, roll it across the table, and if it rolls fine, then it's not bent. If it, you know, kind of lopes down the table, then it itself is bent. I haven't had any bent lead screws at all, I don't think. But it is possible that maybe you bend it or it got bent in shipping. They're usually pretty well packed now. They're usually like inside one of these, but that could be a case. But in my case, this was not parallel to this, and so I had to shim it out to make it parallel. I just used some paper shims that I had, but they actually do have Ender 3 specific shims for the Z-axis that you can print. You can get an STL for them. They're not very thick, so even if your Z-axis is not right, you can use the printer that has the bad alignment to print one of these shims, and it'll go in this spot right here and shim out the Z-axis. I might go ahead and print one of those at some point. Let's see if I can find one real quick. Let's see. Here we go. Here's at least what they look like. There's one. There are some that look like a little bracket that the Z motor will sit in, and it will also have this little spacer. I don't see another. That's usually something like this will solve it, and it's a really quick print if you don't have anything to actually shim out with that. But check that. Check the Z-axis alignment. All right, so those are all hardware things. So those, your firmware doesn't matter. Those you should just do on the hardware itself to make sure that you're going to end up with the best chance possible of having good prints that actually succeed. These others here, these are all software for firmware, calibration, stuff like that. They're all digital. So these will change if you change firmware. So we will change firmware at some point, to a couple of times probably throughout the quarter. I'm just going to show you how to do them, and you can do with them what you want. So this number 5 is extruder calibration. So what that means is, let's get turned around here. What that means is that the amount of filament that I tell, there's a little feeder back here, this little setup back here that feeds the filament into the hot end. It is based on this stepper, so this guy right here, this stepper motor turns a certain amount of steps. So stepper motors they are DC motors, but they're not like the ones that you are mostly familiar with. So you don't just give them power and they start spinning. What you do with them is you give them types of power, like a configuration of power, and they will turn a single or a partial step. So it's like a discrete amount of steps that they will turn. And you have a thing called E steps. So extruder E steps. And what that is, and each firmware does it a little bit differently on how they measure it, but in general, what it is how many steps does it take to extrude a certain amount of filament. So if I want to extrude 1 millimeter of filament, how many steps on this extruder, how many turns or partial turn, you know, little steps in of a turn does it take to get that millimeter to come out? And so tuning your E-steps is one thing that you could do early on. Now, most printers in their default configuration, so you haven't changed anything over here, and you haven't changed firmware or anything. Now, I did change firmware, so mine might be off. But most of the time, when you haven't done any of that, then your E-steps are fine. So if you want to check your E-steps, let's do that. Let's check our E-steps. So I got to turn the printer on. And I'm actually going to, let's get it turned to where, all right, I'm actually going to take this off. Actually, not yet, though. I'm going to retract some filament. There's filament inside here, so I'm going to get some filament out. Let's prepare, preheat for PLA. Oh, no, let's actually control temperature and nozzle temperature. I don't want the bed. I just want the nozzle. We'll deal with the bed later. Actually, in the next, well, we'll talk about it in the next step. Okay. So the nozzle, there's two reasons I'm heating the nozzle. So over on the, you can't see it, but over on the control panel, I just told the temperature of the nozzle to go to 200 degrees Celsius. The actual temperature doesn't matter, except that I want it to be hot enough that it will actually let me remove the filament from here. Most printers will not let you operate the feeder without the extruder heated up, because it thinks that if this is cold and you're trying to push filament through there, something's going to get jammed up and it's not going to work. So most of them won't let you, you can manually turn it, but they won't let you turn it with the control panel if the nozzle's not on. So we're at 170. That's almost enough for what we want to do. All right, 185. Now it'll keep going, but I want to remove the filament that's in here. So how I do that is I go back here and squeeze the lever that releases the drive wheel from being in contact with the filament. And I'm actually going to push the filament through a little bit, so I squeeze out a little bit here, and then I'm going to pull it back out. All right, so there we've got our filament out. Looks reasonable. Got to be careful. I didn't want that little thing on there. That's hot. All right, so I'm going to take this off. I just usually keep mine hand tight because I do unattach it several times. No, you don't want this to be loose though. See these little, let's see if I can find it. These little blue clips right here, a lot of printers don't have those already installed, and you have to snap them on there yourself. You may not think it's not very important, but without these, there's a little bit of a chance that this tube can slide back and forth a tiny bit, like less than a millimeter even. But if you're doing prints that use retraction, we haven't talked about retraction really, but what that means is it's pulling the filament back out. So it's printing and then it's moving somewhere, and as it's moving, it's pulling the filament back up. So that's retraction. If you have slop in this line where it slides back and forth, then that retraction setting is going to be impossible to track to get consistent. So put these little clips in. All right. Now, what I want to do is not do anything to do with retraction. So I'm actually going to unscrew it entirely. I'm going to feed our filament in there. I'm actually going to cut the end off because it's got a spot on it that's not useful. So I'm going to, remember it helps if you cut that at an angle. Usually helps to feed it in if it's a little bit of an angle point. It's also hard to do when I can't get to the printer very well. There you go. All right, so just going to feed it through there. Now I'm going to shear it off flush with that edge. So that's kind of like my 0 point. Some printers you can't do that. We'll talk about those later. All of the printers that most of us have this tube, this Bowden tube, and so you can take the Bowden tube off. And all I'm interested in is, for now, is when I tell this feeder to feed me a certain amount of filament, do I actually get that amount of filament? That's all I'm interested in. So I don't care what's actually coming out of here yet. I just want to know, is it feeding the right amount? So you go over to your control panel over here, and for this printer it's control. Remember, I've got the temperature on the nozzle heated up because most printers won't let you feed filament if this is not heated. So control motion, and no, not maybe it's prepare. Let's see. Prepare move. All right, that's what it is. Prepare in this menu. They're all going to be a little bit different named, but prepare, move, extruder, and I'm going to tell it to extrude these. These are just numbers, but they're millimeters. I'm going to tell it to extrude 100 millimeters. Oh wow, it's counting by 0.1, so that's going to take a while. Let's get over there. All right, there is 100. All right, and now it starts spitting. You don't want it to go too fast, because if you go too fast, there's possibility for slipping and skipping steps and all that. So it's going pretty slow. So it's going to take a while for the 100 millimeters to come out of there. I want to do a relatively large amount, like 100 millimeters, to kind of average out the any errors that it might have in it. And once I get my 100 millimeters out of here, I'm going to cut it off and actually measure it and see if it's 100 millimeters. If you have a printer that doesn't have a tube and this feeder is basically attached to your hot end, you can do the same thing, except what you do is you put a mark on the filament on the other side of the feeder, you know, over here, and you measure how far that mark moves. So it's a little harder to do. This is actually really easy because you just cut this off and measure it. But if you have a direct drive, so one where the feeder is directly feeding filament into the hot end, then you can do the same approach, but you just measure how far it pulled it, basically. Looks like we're getting close. It might have stopped. All right, so that's what it thinks. That's 100 millimeters. So I'm going to shear it off, and I'm going to get my calipers, and I'm going to zero them. They are zeroed. Now it's always going to be curved a little bit, so you got to straighten it out. Doesn't work too well in the air. Like, it's better on a table, but so now what it says is we're actually at 95. Oh, you can't read that. 95 millimeters came out. So I asked for 100 and I got 95. So that means that every time the slicer, so Cura or Prusa slicer or whatever, what it's doing when it is slicing up the material is it is not only telling the printer where to move, but how much filament to feed as it's moving, because it's based on these printers are very dumb. Most all of these printers don't know anything. They know what temperature they are, and that's it. They don't know anything about where things are or how much filament is coming out. They don't have sensors that measure any of that. Certainly not at this price point. They don't have that. Even the really expensive ones don't have much of that. So they're really dumb. So it's all based on the slicer predicting what it needs to do, writing that in G code, the printer reading that G code and just following those instructions blindly. So if the slicer is expecting, when I ask for 100 millimeters, I get 100 millimeters, then and your printer is only doing 95 millimeters, then you're going to have what's called under extrusion. Now, I suspect that this 95 is probably on purpose, because for a variety of reasons that it's a dumb process, right? It doesn't have feedback that tells, there's nothing really that looks at the print as it's happening and says, hey, you ought to adjust these things. There's no feedback like that. So in general, it is dropping your flow rate to 95% of what it is supposed to be generally makes things look better, because it's really hard for these slicers, at least the modern slicers, maybe in the future we'll have this ability, but it's really hard for them to accurately predict when you lay down that filament at a certain layer height and a certain feed rate, how much does it squish out. And it's all just kind of a volumetric calculation. Filament in equals filament out, and that filament should land in these certain spots, but in general a 95% flow rate in the calculations for the slicers looks pretty good. And 100% flow rate sometimes looks like it's putting out too much filament. So I suspect that that's why this printer is hardwired basically to do 95%. Now to change the flow rate, let's see, some printers you can change not the flow rate, the E-steps. So some printers you can do it on the menu here. I don't know if I can or not. Let's see. Maybe in control, motion. Don't. Okay, so it's weird, and it's a translation error. But in what menu am I in? So in this particular menu, it's control, motion. So that kind of makes sense. I'm moving filament. Transmission ratio, and transmission ratio for E. So most of your little menus are going to call that E-steps. But this one calls it transmission ratio for E. And it says that I currently have a value of 93. So I'm reading that off this screen. So currently 93 steps will get me a certain amount of filament, and it's under extruding by 5%. So it's giving me 95 when I ask for 100. So I can adjust that number up 5%. So let's see what that number is. 93 times 1.05, 97.65. So I can go up to 97 point, well, we'll have to do 7. This one doesn't let me do hundredths. So now I've got the E-steps value at 97.7 because I need more. Oh, wait, no, I need to go the other way, don't I? No, I need more steps. I am under extruding, so I need more steps. And I can try it again. So I can go to prepare, move, extruder, ask for another 100 millimeters. I'm sheared off here, and see if I get closer to 100 millimeters now. So that's kind of an iterative process of changing your value based on what percent you actually got, and back and forth until you get it. You don't have to worry about that you got it exactly at 100 when you ask for 100. You just want it close. There's enough variation in... Uh-oh. Wow, something went wrong. I got this much. That is not at all what I wanted. So I wonder... Oh, I wonder if this is cumulative. Let me see. This value in here might be cumulative. So it basically gave me the leftover, the part I didn't get last time, I think, is what it did. Alright. So I guess I need to ask for, let's 0 it. See what it does. Oh, right. So not all the screens are set up this way. This one, the way this particular screen is set up is that the value that it's showing me is a cumulative value. So I ask it for 100 E-steps. So if I, or 100 millimeters, if I want another 100 millimeters, that would be 200. So right now I set it to 0, so it's actually retracting everything, which is annoying, but that's the way it's set up. So we'll let it finish retracting back to 0, and then we'll ask it for another 100, which is not really what we want. So this little piece that it gave here is probably just the 5 millimeters I was missing last time after I changed the E-steps. I know there aren't many concurrent viewers right now, like people watching live, but you have a question while we're waiting for these things to extrude and whatnot, let me know, because we've got a few minutes for it to just sit here and extrude. Alright, so it finished getting back to 0. Let me see if we can, I'm going to resharpen my filament here. Well, it's really quite difficult to get it to want to line up. Might have to get where I can see. Oh, wow. All right. Had to get it a really sharp angle to get it to go in there. All right, so we're going to cut it back flush. We're going to ask for our 100 millimeters. Oops. And see what we get. Okay. While this is going, let's talk about some of our printer calibration tests. So there are 3 in particular that I asked you to do for the course. One of them is a temperature tower. So that will look like, where do I have my temperature tower? That will look like this. The point of this thing is every filament is slightly different when it comes to what temperature it prefers to print at. Some have a really wide range of temperatures, some have a narrow range that work well, some work over a wide range, but they have different surface finishes at different temperatures. Like one of them might be matte at a higher temperature and glossy at a lower temperature, or vice versa. So these little things help you figure out for that particular roll of filament And usually other rolls from the same company that are the same color and same, everything, will be pretty similar. And there aren't too many filaments that, most PLA you can put 205 and print fine at it, but if you're looking for a very particular thing, these will tell you by you reading it what is the best temperature to print at for what you're trying to get. So what this does is it starts out at the highest temperature you want to do. So this one starts at 210, and then it drops by, I don't know, usually it's 5 degrees per little section there, and it'll print. So it'll print a section at 210, then it'll print the next section at 205, and so forth. And you're looking for, well, where is the print? This one doesn't have too many problems. All the little bridges worked. Now this very top one, you can't really tell. I can see up close that it's a little bit droopy compared to the others, but the underside of these overhangs looks good. The surface finish looks good everywhere. So they're all, relatively, none of these are really weak. None of them are just snapping off. Sometimes you get too low and it'll snap, or too low and it won't even print. Too high and it's just gummy, and it's really wobbly, or not wobbly, but lumpy. This one looks like most any temperature between 190 and 210 will print well. Now you have to pair that with how fast are you printing. So if you are trying to print at a little higher speed, then you need a higher temperature because you've got to melt plastic faster. And so you kind of do have to pair this with what speed do you want to print at. Because I could print this at a slow speed and it looks one way, and then I could try to do nothing except change the speed, print faster, and some of these colder temperatures probably aren't going to work out as well, because it can't melt the filament fast enough. So you do have to think about that, but that's these temperature towers. We did get our filament here, so let's see what we got. So we asked for 100 millimeters, and let's see what we get. We upped our, or we were down by 5%. We asked for 100 and got 95. Now we have, looks like 102. 102. So we got a little bit more than we want. So what I'm going to do is I'm going to drop our E-steps slightly. So this is one of those things that you can chase it back and forth. I'm not going to worry too much. We were at, let's see if it's still on my calculator. Nope. I think we were at 94.3. Is that what it was? No, 93.4. I don't know. We were around 93 or something. I don't remember what the number was. Should have written it down. I think we're at 93.1 or 93. We were right around 93. Maybe it was 93. I think it was. Yes, we were at 93. And I bumped it up 5% because we were 5% short. And now we're 2% whatever long. So I'm going to drop down to 95. Actually, let's do 95 and a half. So I could sit there and, chase back and forth until I get exactly 100, but I'm pretty sure that we're pretty close. So I'm going to leave it where it's at. Now, I have it built into here now, but there is normally a store command that actually stores that value. So I'm going to click that, get a little beep, and that means that it has stored that value that I changed into the printer. If I don't click store, then I turn the printer off, turn it back on, it goes back to the previous value, that 93 number that was 5% short. Okay, let's see where we're at. Got another 15 minutes, so let's do some other stuff. So E-steps, you can normally adjust those on the printer itself through the control panel. This next one, let's look at some other stuff now. PID tuning. So PID, I've got a whole little write-up. Where's it at? PID tuning walkthrough. I've got a whole write-up here about what this is. So PID, that's an acronym for proportional, integral, and derivative. Actually, if you scroll down, I've got it kind of broken out what those mean down here. But this is a control system for things like temperature. And again, the printers are dumb except for the temperature. They know the temperature of the bed and the nozzle. That's basically all they know. Everything else is they're guessing based on where it should be. So they do have a control system. You've got a thermistor at the basically right at the nozzle. A thermistor is a resistor that changes temperature or changes its resistance with temperature changes, and you can measure it. So it's basically a way to measure temperature. And this control system, PID, takes the proportional approach where maybe my set point is 200 degrees Celsius and I'm at 100 degrees Celsius, and it takes that delta, the 100 degrees between where I am and where I want to be, and it makes your gain proportional to that change, that delta. That's one control system. That one usually causes a lot of overshoot because you're really far off at the beginning, and so you get a bunch of gain, a bunch of heat going into the system, and then it way overshoots the set point, and now it's too high and it turns it off, and so you just end up oscillating back and forth if you only have proportional. So it also adds integral. So integral is what you might think, if you know any calculus, that it integrates. And so it is integrating over time what has been happening. So it takes into the account that, well, I've got the area under this curve. That's what integrating does, is it calculates the area under the curve. So that I've got all this energy, heat energy. I can predict that that's going to also have like Newton's law of cooling and heat transfer and all this kind of stuff. So if I only rely on proportional, I'm going to way overshoot. But if I know the past history, then I can kind of control that. And it adds the D part, the derivative, same thing, except now I'm looking at the rate of change, so the slope of the line. So it's predicting where it will be based on the current rate. And so you combine proportional, integral, and derivative control, and you get a much more stable control system. The proportional by itself, where it's just I'm off by this much, I'm going to crank up the heat, and then I get way overshoot and I turn off the heat, that's called bang bang. Your printer bed probably has bang bang tuning on it. If you notice, by the way, so a little aside on that, if you notice your prints are coming out and they have these kind of stripes in them, like maybe it's not necessarily that they're very noticeable, but they have these bands in them, it could be that the bang bang tuning on the bed is causing the bed to basically, at a really, sub-millimeter level, switch between two states, a curved state and a kind of flatter state. And it's doing that when it's on, it's deformed and bent up maybe, and then when it's off, it goes back flat, sub-millimeter level. But what that's doing is now if your print is on top of that surface that's curving up and then flat, up and flat, up and flat, it is bringing it closer and further away from the nozzle periodically at the same rate of your bang bang tuning, your on and off heater on your bed, and you'll get these little bands that are relatively periodic, and they'll just show up as these strange layers in your print. And most of your beds do. You can turn PID tuning on most of the beds, but most of them usually start with bang bang. So if you notice those little stripes, that could be the cause. Your printer nozzle does do PID tuning. Most of the time you can't do PID tuning through the printer's control panel. There might be some that you can. I actually know there are some that you can. And that's a much easier process. This printer doesn't let me do that as far as I can tell. Yeah, I don't see anything. Yeah, I don't see anything here that lets me do PID tuning on the control panel. So if you have a printer like me that, and with firmware that doesn't let you do PID tuning on the printer, then you got to do a couple of things. So first I'm going to turn the printer off. I'm going to get USB cable, but not just any USB cable. So I need to be able to communicate with the printer. So I need a data USB cable, not just one that's power. This one is data. You can usually tell the data ones, maybe they have this little thing on them for signal conditioning, but I don't even know if that's universally true, but it's generally true. So I'm going to plug my printer in to my computer. Let me make sure that Cura and all my slicers are off. Yes. If you have Cura running when you do this, Cura is going to take over and you're not going to be able to do what we want to do. So, all right, I heard the little ding that it says it connected. The printer main power is off. So I turned the main power off, but its screen came on. I don't know if you can kind of tell it there. The screen came on. So it's getting power and now it's sending data back and forth when I ask it to. But it's getting power enough to turn the screen on, but not actually do anything. It doesn't, the USB is not, it's like 5 volts and I don't know, a couple of 100 milliamps maybe. But it's not enough to like move motors around really or anything like that. Definitely, it might move a motor, but it's definitely not going to heat the heater for the nozzle. What I do have is I have this piece of software. Uh-oh. No, I might have a problem displaying. Let me real quick. This little fan right here came on because that fan's going to be on most of the time while I'm printing. So I've got it on. All right. Now let's go back to our printer face. piece here. This is a light cover for an older car that they don't make replacements of these, and they get really brittle. You know, there's a little light bulb inside here and they get brittle. We're going to try and scan this thing and print it, a replacement part. So we're going to try and do that. It'll have some challenges. I don't know how well we'll be able to do it, but I don't know, we'll figure. I do have a little handheld scanner that we'll look at, and there are some materials that'll probably hold up under the heat of, there's, you know, an incandescent light bulb goes in there that's going to be pretty hot, and PLA probably won't survive that. But we have other materials we can deal with, so we're going to see, you know, if we wanted to make one of these, how close could we get with reasonable approaches. All right, so we'll be back on Friday, and I don't know if we'll start this project on Friday. We might, but we'll get into some printing, maybe some different materials or whatever, or if some particular questions pop up between now and then, we'll try to answer those. But I'll see y'all on Friday.